We're now moving on to Newton's second law of motion, which deals with unbalanced forces. So once again, here are Newton's three laws of motion. The first one, law of inertia, we've covered. So the law of inertia states that an object that has constant velocity stays that way unless a net force acts on it. And so, what happens when a net force acts on it? Well, the object, well, in this case, will be out of mechanical equilibrium, right? And so you will start accelerating in the direction of the net force. So this is what we will be looking at today. I've actually alluded to this law back in the first video, remember F01, I think, but I said not to worry about it. Well, now it's time to worry about it. In the second law, Newton basically states the relationship between force, mass, and acceleration. But, well, this formula that you see right here is actually worked out by a mathematician called Euler. F equals ma, force equals mass times acceleration. The more massive the object, the greater the amount of force you're going to need to achieve the same acceleration. And for a given mass of the object, if you want to have a greater acceleration, well, you increase the force. And that makes sense, doesn't it? I mean, if you're more massive, you have higher inertia, so it's harder to make you change your velocity. Now, let's work through a common problem. Okay, this is an object sliding on a slope. We have a kind of a cutesy problem here. We have a penguin who's playing on an icy slope. How's that? He's sliding down a slope like this. Whoosh, boom. Okay. So it's an icy slope, so it has no friction. Let's just say that. And the penguin has a mass of, let's give it 10 kilograms. Now, we also need an angle for the slope. And for this question, we'll say it's 35 degrees. Okay. Let's first draw in the forces acting on the penguin. We obviously have weight that's always acting downwards. And we can quickly calculate that. This equals to mg, right? Mass times acceleration due to gravity, 9.81 meters per second squared, times 10 kilograms. Just a quick calculation, that's 98.1 newtons. Next, we also have the normal force. But since the normal force has to be perpendicular to the surface, and in this case the surface is at an angle, essentially we have a surface that is tilted clockwise by 35 degrees. Well, our normal force would also have to be equivalently tilted by 35 degrees in a clockwise direction. So we have this. Now, I really have two options when setting up a coordination system. Remember what I said before, that a coordination system can be set arbitrarily as long as it's consistent. So choice number one would be to set it up like what we did before, I guess, that being positive. Now that would mean I would have to break the normal force into its a y and a x component, and the weight force would be lying on the axis. Choice number two is to set the coordination system this way, basically tilted 35 degrees clockwise, so that now we have the slope lying on the axis. In the second case, normal force is now lying on the axis and the weight force is not. So we're going to have to break the weight force down into its this new x and y components. Now we want to use the second coordination system. And that's the case for most slope problems. And you'll quickly find out why later on. So for this one, we're going to use that one. Now we'll have to break down the weight, right? Now we want the weight to be expressed as these component forces that lie on the axis that we've set. So we have weight going like this and going like that. That's 90 degrees. That's weight in the y direction. That's weight in the x direction. Now we know we've flipped this 35 degrees from the vertical line, so we have 35 degrees over here, which makes this one 35 degrees. Now I need to remind you why this is 35 degrees is over here and over here. Well, remember we flipped the axis by 35 degrees from the horizontal. That means in terms of the vertical line, our normal force will now also be flipped 35 degrees, tilted 35 degrees clockwise. And so by opposite angles, we have 35 degrees and 35 degrees. Great, so now I have an angle, and I have the magnitude of the hypotenuse, which is 98.1. We can use trigonometric ratios to find the component magnitudes, right? And I've already done this. I'll just write the results down. Sorry for the handwriting, by the way. I've been working on it. It doesn't seem to be improving very much. Now, let's look at it in components again. What is the force like, the net force like, in the y direction? Well, remember we have a new axis over here, and seeing that the penguin is only moving like this, right? So in the x direction, according to our coordination system, and it's not moving up and down like that. So that must mean in the y direction, our net force is 0. No acceleration whatsoever. Which must mean normal force is balanced out by the y component of the weight force. And so those are the same values of 80.4 newtons. However, what about in the x direction? Well, the penguin is sliding down the slope, right? And what's the force compelling it to accelerate down the slope? Well, it's none other than the force of gravity, which is a weight force, in the x component, because that's the only force that's acting in the x component, actually. And that's 56.3 newtons. 56.3 newtons. That's the net force in the x direction. Now, we know that's equals to mass times acceleration. I can also say acceleration in the x direction in this case, just to be very specific. And we know that it's equal to 10 kilograms multiplied by the acceleration. So the acceleration is 56.3 newtons divided by 10 kilograms, giving us 5.6 meters per second squared-ish. And that's how fast the penguin is accelerating down the slope. Okay, I hope you had fun there. See you next time.